Gallium arsenide is a compound of the elements gallium and arsenic. It is a 3V direct bandgap semiconductor with a zinc blende crystal structure. Gallium arsenide is used in the manufacture of devices such as microwave frequency integrated circuits, monolithic microwave integrated circuits, infrared light-emitting diodes, laser diodes, solar cells and optical windows. GaAs is often used as a substrate material for the epitaxial growth of other 3V semiconductors including indium gallium arsenide, aluminum gallium arsenide and others. Preparation and chemistry. In the compound, gallium has a +3 oxidation state. Gallium arsenide single crystals can be prepared by 3 industrial processes, the vertical gradient freeze process. Most GaAs wafers are produced using this process. Crystal growth using a horizontal zone furnace in the Bridgman-Stockbudger technique, in which gallium and arsenic vapors react, and free molecules deposit on a seed crystal at the cooler end of the furnace. Liquid encapsulated Czochralski growth is used for producing high-purity single crystals that can exhibit semi-insulating characteristics. Alternative methods for producing films of GaAs include VPE reaction of gaseous gallium metal and arsenic trichloride, 2 Ga plus 2 as Cl, 3 A 2 GaAs plus 3 centiliters, 2, MOCVD reaction of trimethylgallium and arsine, Ga, Ch, 3, 3 plus ash, 3 A GaAs plus 3 Ch, 4, molecular beam epitaxy of gallium and arsenic, 4 Ga plus as, 4 A 4 GaAs, or, 2 Ga plus as, 2 A 2 GaAs. Oxidation of GaAs occurs in air and degrades performance of the semiconductor. The surface can be passivated by depositing a cubic gallium, 2, sulfide layer using a tert-butyl gallium sulfide compound such as 7. Semi-insulating crystals. If a GaAs boule is grown with excess arsenic present, it gets certain defects, in particular arsenic antizite defects. The electronic properties of these defects cause the Fermi level to be pinned near the center of the bandgap, so that this GaAs crystal has very low concentration of electrons and holes. This low carrier concentration is similar to an intrinsic crystal, but much easier to achieve in practice. These crystals are called semi-insulating, reflecting their high resistivity of 107 A 109 ICM. Etching. Wet etching of GaAs industrially uses an oxidizing agent such as hydrogen peroxide or bromine water, and the same strategy has been described in a patent relating to processing scrap components containing GaAs where the Ga3+ is complexed with a hydroxamic acid, for example, GaAs plus H, 2O, 2 plus HA a GaA complex plus H, 3 is O, 4 plus 4 hours, 2O. This reaction produces arsenic acid. Comparison with silicon. GaAs advantages. Some electronic properties of gallium arsenide are superior to those of silicon. It has a higher saturated electron velocity and higher electron mobility, allowing gallium arsenide transistors to function at frequencies in excess of 250 GHz. Unlike silicon junctions, GaAs devices are relatively insensitive to heat owing to their wider band gap. Also, GaAs devices tend to have less noise than silicon devices, especially at high frequencies. This is a result of higher carrier mobilities and lower resistive device parasitics. These properties recommend GaAs circuitry in mobile phones, satellite communications, microwave point-to-point links and higher frequency radar systems. It is used in the manufacture of GaN diodes for generation of microwaves. Another advantage of GaAs is that it has a direct band gap, which means that it can be used to absorb and emit light efficiently. Silicon has an indirect band gap and so is relatively poor at emitting light. Nonetheless, advances silicon LEDs and lasers may be possible. As a wide direct band gap material with resulting resistance to radiation damage, GaAs is an excellent material for space electronics and optical windows in high-power applications. Because of its wide band gap, pure GaAs is highly resistive. Combined with the high dielectric constant, this property makes GaAs a very good electrical substrate and unlike Si provides natural isolation between devices and circuits. This has made it an ideal material for microwave and millimeter wave integrated circuits, MMICs, where active and essential passive components can readily be produced on a single slice of GaAs. One of the first GaAs microprocessors was developed in the early 1980s by the RCA Corporation and was considered for the Star Wars program of the United States Department of Defense. Those processors were several times faster and several orders of magnitude more radiation-hard than silicon counterparts, but they were rather expensive. Other GaAs processors were implemented by the supercomputer vendors Cray Computer Corporation, Convex, and Alliant in an attempt to stay ahead of the ever-improving CMOS microprocessor. Cray eventually built one GaAs-based machine in the early 1990s, the Cray 3, but the effort was not adequately capitalized, and the company filed for bankruptcy in 1995. Complex layered structures of gallium arsenide in combination with aluminium arsenide or the alloy AlXGa1Xs can be grown using molecular beam epitaxy or using metal-organic vapor phase epitaxy. Because GaAs and ALUs have almost the same lattice constant, the layers have very little induced strain, which allows them to be grown almost arbitrarily thick. This allows for extremely high-performance high-electron mobility, HEMT transistors and other quantum world devices. Silicon advantages. Silicon has three major advantages over GaAs for integrated circuit manufacture. First, silicon is abundant and cheap to process. Si is highly abundant in the Earth's crust, in the form of silicate minerals. The economy of scale available to the silicon industry has also reduced the adoption of GaAs. In addition, a Si crystal has an extremely stable structure mechanically and it can be grown to very large diameter boules and can be processed with very high yields. It is also a decent thermal conductor, thus enabling very dense packing of transistors that need to get rid of their heat of operation, all very desirable for design and manufacturing of very large ICs. Such good mechanical characteristics also makes it a suitable material for the rapidly developing field of nanoelectronics. The second major advantage of Si is the existence of a native oxide, which is used as an insulator in electronic devices. Silicon dioxide can easily be incorporated onto silicon circuits, and such layers are adherent to the underlying Si. CO2 is not only a good insulator, but the Si-CO2 interface can be easily engineered to have excellent electrical properties, most importantly low density of interface states. GaAs does not have a native oxide and does not easily support a stable adherent insulating layer. Aluminum oxide has been extensively studied as a possible gate oxide for GaAs. However, at this point the electrical properties of the interfaces aren't comparable to those of the Si-CO2 interface. The third advantage of silicon is that it possesses a high hole mobility compared to GaAs. This high mobility allows the fabrication of higher-speed p-channel field effect transistors, which are required for CMOS logic. Because they lack a fast CMOS structure, GaAs circuits must use logic styles which have much higher power consumption. This has made GaAs circuits less able to compete with silicon logic circuits. For manufacturing solar cells, silicon has relatively low absorptivity for the sunlight, meaning about 100 micrometers of Si is needed to absorb most sunlight. Such a layer is relatively robust and easy to handle. In contrast, the absorptivity of GaAs is so high that only a few micrometers of thickness are needed to absorb all of the light. Consequently, GaAs thin films must be supported on a substrate material. Silicon is a pure element, avoiding the problems of stoichiometric imbalance and thermal unmixing of GaAs. Silicon has a nearly perfect lattice, impurity density is very low and allows very small structures to be built. GaAs in contrast has a very high impurity density, which makes it difficult to build integrated circuits with small structures, so the 500 nm process is a common process for GaAs. Other applications, solar cells and detectors. Another important application of GaAs is for high-efficiency solar cells. Gallium arsenide is also known as single crystalline thin film and are high-cost high-efficiency solar cells. In 1970, the first GaAs heterostructure solar cells were created by the team led by Tzors Alferov in the USSR. In the early 1980s, the efficiency of the best GaAs solar cells surpassed that of silicon solar cells, and in the 1990s GaAs solar cells took over from silicon as the cell type most commonly used for photovoltaic arrays for satellite applications. Later, dual and triple junction solar cells based on GaAs with germanium and indium gallium phosphide layers were developed as the basis of a triple junction solar cell, which held a record efficiency of over 32% and can operate also with light as concentrated as 2000 suns. This kind of solar cell powers the rovers Spirit and Opportunity, which are exploring Mars' surface. Also, many solar cars utilize GaAs in solar arrays. GaAs-based devices hold the world record for the highest efficiency single-junction solar cell at 28.8%. This high efficiency is attributed to the extreme high-quality GaAs epitaxial growth, surface passivation by the GaAs, and the promotion of photon recycling by the thin film design. Complex designs of ALX-GA10X GaAs devices can be sensitive to infrared radiation. GaAs diodes can be used for the detection of X-rays. Light-emission devices. GaAs has been used to produce laser diodes since 1962. Safety, the environment, health and safety aspects of gallium arsenide sources and industrial hygiene monitoring studies of metal organic precursors have been reported. California lists gallium arsenide as a carcinogen. However, there is no evidence for a primary carcinogenic effect of GaAs. See also. References. External links, case studies in environmental medicine, arsenic toxicity, physical properties of gallium arsenide, facts and figures on processing gallium arsenide.